Good morning, grade 11s. We continue with our lesson on intermolecular forces. Now, just to remind you what we've covered so far, we've had a look at London forces, and London forces happen in all particles. And remember that London's forces are the weakest intermolecular force. It is the only intermolecular force between non-polar molecules and noble gases. And remember, it is from the production of temporary dipoles because of the movement of electrons, and those temporary dipoles induce dipoles in the next noble gas or the next particle. Then we went on to dipole-dipole forces, and that is between polar molecules. So polar molecules have London forces, but they have a much higher boiling point because they also have dipole-dipole forces which are stronger. So remember, another name for a polar molecule is a dipole. And to determine whether a molecule is polar or not, we first have a look at the intramolecular force, the bonds, and then we look at the overall molecule and see if we've got a symmetrical or asymmetrical distribution of charge due to its shape. The next one we're going to have a look at is a specialized dipole-dipole force called a hydrogen bond. And the three, London forces, dipole-dipole forces, and hydrogen bonding, fall under what I told you in the last lesson are called van der Waals forces. As we move into hydrogen bonding, I'm going to continue speaking about dipole-dipole forces because hydrogen bonds are specialized dipole-dipole forces. I'd like to look at the trends in the group 6 hydrides. So group 6 on the periodic table is sulfur, selenium, beryllium, and oxygen. And hydrides are when they are bonded to a hydrogen. So if we have a look at the boiling points, we can see H2S is minus 60, H2SE is minus 41, and H2TE is minus 2. So if those are plotted onto a graph, we can see a trend. So from H2S, as we move up to H2TE, the boiling point increases. Now, if we were to look at the intermolecular force between these three molecules. So H2S, that's held together in liquid, would be London forces because there's London forces in everything, but it would also have dipole-dipole forces. The H2SE would have London forces and dipole-dipole forces. The H2TE would have London forces and dipole-dipole forces. So now they all have exactly the same intermolecular forces. So why is there a difference in boiling point? So remember what I told you have to have a look at. If you've got the same type of intermolecular force, we have to look at either the surface area or we would look at the molecular mass. So in this case, we look at the molecular mass. As you go from H2S to H2SE to H2TE, the molecular mass is increasing. If the molecular mass increases, then we know the electron cloud density increases, which results in an increase in the strength of the intermolecular forces, and therefore more energy is required to break the intermolecular forces, and therefore the boiling point increases. Now H2O has the lowest molar mass in this group. So if we were looking at the trend, water should be down here somewhere at about minus 90 degrees Celsius for the boiling point because it has the lowest molecular mass of the group 6 hydrides. But surprisingly, we know that the boiling point of water is 100 degrees Celsius. So it is way higher than even H2TE, which is the heaviest in the group. So this means there must be a different type of intermolecular force, a stronger intermolecular force. and that is what we call a hydrogen bond. Before I get into the nitty-gritty of the hydrogen bond, I'd like to look at the shape of each of these group 6 hydrides. So if the red atom here represents the group 6 element, so example the S or the Se, the Te or the O, and the blue represents the hydrogen. So there's a difference in electronegativity between the elements in group 6 and the hydrogen, and so we get a polar covalent bond. So we get a slightly positive and a slightly negative side to the molecule. And also, because it's in group 6, we've got these 2 lone pairs. And because of those 2 lone pairs, the lone pairs repel the electrons in the bond. And so what happens, it's not a linear molecule, it is an angular molecule. So when it's an angular molecule, you can see there's a concentration of electrons over here towards the group 6 element. And so there's an asymmetrical distribution of charge. So we have a dipole and it's an angular molecule. And so the intermolecular force we're talking about would be the electrostatic attraction between the slightly positive end of the molecule and the slightly negative side of the molecule. Now, if we look at each of the molecules and their molecular mass, you can see as we go from H to S, it's 34, to H to Se, it's 81, H to Te, it's 130. They're all polar angular molecules. Angular because of these lone pairs that repel those shared electrons to make it angular. Then all 3 of them have London forces and dipole-dipole forces. The main intermolecular force being the dipole-dipole because that's the stronger one. And so the trend from the lowest molecular mass, the H2S to H2Te, the strength of the intermolecular forces increases, and therefore the boiling point increases. And then we have water, and water is way above what we would expect for the boiling point. So it means we have a much stronger intermolecular force. And so it has the same shape as discussed over here. It will have London forces because London forces are in everything, but the dominant, stronger, specialized dipole-dipole force is called the hydrogen bond. And the hydrogen bond is much stronger than a regular dipole-dipole. So it requires way more energy to overcome the hydrogen bond, and therefore the boiling point is 100 degrees Celsius, much higher than expected. So how do hydrogen bonds come about? So, as I told you, the hydrogen bond is a special case of dipole-dipole. So, it's between polar molecules, but there's another 2 criteria that have to be met. Obviously, if it's hydrogen bonding, there has to be a hydrogen, but the hydrogen atoms bond covalently to a small atom with a high electronegativity. So, within the original molecule, the hydrogen has to be bonded to either a nitrogen, an oxygen, or a fluorine. That's within the original molecule. And that is because the nitrogen, oxygen, and fluorine have a high electronegativity and they attract that shared pair of electrons very strongly. So if we look at HF over here, there's a large electron cloud density around the fluorine atom because there's a very unequal sharing of electrons over here. There's very little electron cloud density around the H atom. So we've got quite a strong, slightly positive side over here. And so when that hydrogen bonds to the next HF molecule, the hydrogen would be attracted to the fluorine in the very next molecule. And because it's quite a strong positive charge, and the fluorine has quite a strong, slightly negative charge, it makes for a much stronger bond than a regular dipole-dipole. And obviously, you have to have polar molecules because it's a specialized dipole-dipole. And dipole-dipole occurs between polar molecules. So if we look between water over here, so within the water molecule, between the oxygen and the hydrogen, there's a polar covalent bond. There's an unequal sharing of electrons. So most of the electron cloud density is around the oxygen, and there's very little left around the hydrogen. And so it's almost just a proton here by the hydrogen, and that is very attracted to the slightly negative oxygen over there, and that in the next molecule, and that forms a stronger hydrogen bond. So it's much stronger than a normal dipole-dipole. So the two criteria are the hydrogen within its own molecule has to be attracted or attached or bonded to a nitrogen, oxygen, or fluorine, because they have a high electronegativity and they're going to strongly attract the shared pair of electrons. Then it obviously has to be a polar molecule because it's a special case of dipole-dipole. So when we look at water and we look at the intermolecular force between two water molecules, remember we must look at two criteria. Is the intermolecular force between two polar molecules, because it's a specialized dipole-dipole? Yes, water is a polar molecule. The next water molecule is also polar. So criteria number 1 is fulfilled. Within the molecule, is the hydrogen bonded to a small, highly electronegative element, either nitrogen, oxygen, or fluorine? Yes, the hydrogen is bonded to an oxygen. So the criteria are met. So between oxygen molecules, there's a stronger hydrogen bond. It's a specialized dipole-dipole. Let's look at ammonia. So ammonia is NH3. Ammonia has a pyramidal shape. There's an asymmetrical distribution of charge, so it's a polar molecule. So the next ammonia molecule is also a polar molecule. So the first criteria is met. Then within the molecule, is our hydrogen bonded to either a nitrogen, oxygen, or fluorine? Yes, it is. It's bonded to a nitrogen. So that means the shared pair of electrons are very close to the nitrogen. So that slightly negative charge is higher than normal. And in the next molecule, that slightly positive charge is higher than normal. So the attraction between them is the specialized dipole-dipole called the hydrogen bond. And because the hydrogen bond is stronger than a normal dipole-dipole, then we have to add more energy to break the bond. And so it has a higher boiling point. Water and ammonia will also have London forces, but because the London forces aren't as strong as the hydrogen bond, it's the strength of the hydrogen bond that determines the boiling point. Then if we have a look at an alcohol. Now alcohols, and you'll learn about it in organic chemistry, are molecules made of carbon and hydrogens, and they have an OH group attached to it. Now whenever you've got an OH group in one molecule and it's bonded to another molecule that is the same, because the hydrogen within the alcohol, within the molecule, the hydrogen is bonded to an oxygen, then that fits the criteria. So this part of the molecule is polar. In the next molecule, this part of the molecule is polar. So then we've got the dipole-dipole criteria met. Then within the molecule is the hydrogen involved in the hydrogen bond within the molecule attached to an oxygen, nitrogen, or fluorine? Yes, it is. It is attached to the oxygen. So the slightly positive hydrogen in the one molecule will be attracted to the slightly negative oxygen with a stronger hydrogen bond than the normal dipole-dipole force. Now you can see that these hydrogens I've covered in yellow. Why can't those hydrogens make hydrogen bonds throughout the rest of these two molecules? And the reason is it doesn't fit the criteria. So the side that is just made of carbons and hydrogens, remember I told you, those are non-polar. So it has a non-polar side to this molecule. Also, within the molecule, the hydrogen is bonded to a carbon. The hydrogens that are bonded to carbons are not bonded to an oxygen, nitrogen, or fluorine, so they are not involved in hydrogen bonding with the next molecule. So the ones that I've covered in yellow are not involved in hydrogen bonds since they are bonded to carbon within the molecule. They're not bonded to an oxygen, a nitrogen, or fluorine, which are small, highly electronegative elements.